So let's go ahead and get started again. So we are going to be looking at our Lab 11. There we go. Okay. So looking at Lab 11, so there's a lot of stuff going on here, so I wanted to make a little summary of what I want you to turn in. So for this lab, for part 1, you're going to have 3 graphs. So you'll have 1 for each trial, and you're going to calculate C-Cal 3 times. Again, once for each trial. For part 2, there's going to be 2 graphs. So there was 2 experiments that would have been run in part 2. And so you'll do 1 graph for each of those reactions, and then you'll calculate delta H twice. Again, once for each of those reactions. Then you're going to calculate delta H of formation. You'll also calculate your percent error. There's no lab discussion questions, and I should note on here that I do want you to write the, complete your data sheet. So write the data. So just like always, I want you to copy the data down from the sample data onto your data sheet, and then you're going to complete the bottom part that is going to be the calculations that we talk about right here. And make sure data is always written in pen. So just to take a quick look at your sample data, so this is up on Canvas right now in the lab notes section. And so here is all your data. So this would have been a 2-day lab. In day 1, you would have calibrated a calorimeter. So here is data that you would have gotten for 3 trials. You would have found the temperature at minute 0.5 all the way to minute 5. And then your calculations go down here at the bottom. So as always, if you don't have a data sheet, then I'll have you just write this on a piece of paper. Here is part 2, so this is what you would have done on day 2. And in class, I would have given you calcium for your metal and calcium oxide for your metal oxide. And importantly, this right here is the mass of calcium only. It's kind of confusing because above it says metal plus HCl. That metal plus HCl is just telling you that's the reaction that it is. It is a reaction of your metal with HCl, but the mass is only the mass of the metal. And then over here, this is the mass of calcium oxide only. Even though it says metal oxide plus HCl above, that's just telling you that that's the chemical reaction going on. And again, you're going to be measuring temperatures through here. So we have some really great videos. One of our instructors did a great job recording a demo, and another one did a great job recording an introduction. So I want to have you watch those quickly. Interestingly, when I was watching the demo, I was like, wow, she gets so excited about chemistry. And then I realized that I do the same. Okay, so let me pause this.
Thermochemistry. So this is the section where we show you what we actually do in the experiment, the wet chemistry. And we need to make our calorimeter, which we make out of 2 large styrofoam cups, a lid, tin foil, aluminum foil, pardon me, which goes on top. And then, here's the fun part of the experiment. Oh no, it didn't work. Punch a hole in the lid. There. Whoa. There we go. Okay, so that's our calorimeter. And we actually need 2 thermometers because for the calibration, we're going to be mixing 50 milliliters, 50.00 milliliters of room temperature water with 50.00 milliliters of water that we have just poured off of ice. The 2 will mix. And the interesting thing is, they will not, as they mix, come to the temperature that's exactly in the middle, because the calorimeter will absorb some heat. Actually, I should say the calorimeter will provide some heat. So, that said, let us first pour in 50 milliliters of room temperature water for this calibration. Okay, we let that settle a bit, swirl around, and read the thermometer to the tenth of a degree. The ice water, I have actually just poured off the water from a slurry of ice and water. We don't want any wet ice in there because that would absorb some heat as it melts. And we read the temperature of the ice water, which is nice and cold, but not really quite zero because it's no longer in contact with the ice. Okay, so when we're ready to start the experiment, we pour in the ice water and start the timer. Now, we don't take a temperature reading right away. We wait 30 seconds, then we take a reading, continuously swirling as we're waiting for the 30 seconds. And then we take temperature readings every 30 seconds or so for about 5 minutes. You will see with the calibration that the temperature levels off rather quickly to get the final temperature. Okay, so that was calibration, and since it's just water, we toss it down the drain. Reactions, on the other hand. Okay, we will have in our calorimeter the stated volume of liquid and either pour in another liquid or a solid. And in this case, the liquid that we're using is hydrochloric acid for the Chem 1A experiment, or for the Chem 1B experiment, well, there's one with hydrochloric acid and then there is one where you have water. But in either case, measure out the required volume of liquid. And pour this into the calorimeter. Okay. Swirl a bit, let it equilibrate. Read the initial temperature of the liquid in the calorimeter. And then get ready. Slide in the measured amount of solid. And start swirling. Start the timer. After 30 seconds, start reading the thermometer. Read it every 30 seconds for about 7 or 8 minutes. Okay? That will give the reaction enough time to have temperature, have heat flow, so the temperature of the liquid will go up and then level off and go down. Okay, so that's basically the calorimetry experiment. There is one additional temperature that needs to be taken, preferably around the time that you're doing the calibrations. And that is just simply room temperature of the air. Okay, so that is the end of the experimental video. And you'll get a separate video of calculations. Thanks.
Hello students, welcome back. Dr. DA here. In this activity, we're going to be studying calorimetry and the application of Hess's law. This is experiment number 11 in your lab manual. So please have your lab manual pages with you beginning on page 36. And let's talk about what the experiment is about, okay? Let's go here to our makeshift doc manager and let's see what this is going to be about. So we are interested in the reaction that represents the formation of a metal oxide. It's generic here, but what we're dealing with here is a metal from group 2, like magnesium, calcium, those kind of elements. reacting with oxygen to form the oxide of the metal. This is balanced so as to yield 1 mole of the compound from its component elements in their standard states, which is why we sometimes have to use a fractional coefficient so that the coefficient on the product will be 1. We are interested in finding out what is the enthalpy of this reaction, because since this is a formation reaction, that would be the standard enthalpy or heat of formation of the metal oxide. Now, if we try to do this in the lab, we'll encounter a couple of problems. Number one, the reaction is too exothermic. As a matter of fact, for magnesium, the burning or combustion of magnesium essentially produces not only a lot of heat, but a very bright white light. That's what photographers used in the old days to produce flash so they could take pictures in the dark. It's also a difficult reaction to do in the lab because it's not easy to handle oxygen gas to do a calorimetry experiment. And we don't have a bomb calorimeter to work with. So what we do in these cases is we're going to assemble a fictional reaction path. We're going to choose a set of reactions for which we either know or we can measure the delta H. And we're going to arrange them in such a way that when we add them up, the result is the reaction we're looking for. This is Hess's law, which basically says that the enthalpy of a reaction is the same regardless of how many steps it is done in. Or another way of saying it is that for a chemical reaction, the enthalpy is not dependent on the path of the reaction or the steps that it takes or the mechanism that it takes. It just depends on the initial and final states. So we're going to do this to find delta H for this metal oxide. All right. If you look at page 36 of your lab manual, you'll find this page. And what I'm going to do is I'm going to pull out these equations that are in here for us to explore them very quickly here. Okay. So these are the 4 equations that we're talking about. And let's see what our strategy is. First of all, this equation number 4, that is our target. That's the one we're trying to reach because that's the formation reaction for the metal oxide, all right, for which the enthalpy is the enthalpy of formation of the metal oxide. So when you try to apply Hess's law, what you do is you find a set of reactions that you can organize or arrange in a way that, just like in an algebra set of equations, the quantities or items you want to eliminate are on opposite sides of the equation sign, in this case the arrow, and you can cancel them out so that at the end you have the reaction you want. So first thing we look for is, do we have a reaction where the metal is already a reactant? That would be reaction 1. So I'm just going to copy reaction number 1 over here, and that is the metal reacting with HCl aqueous, which is hydrochloric acid, to produce a chloride of the metal, dissolved in water, and hydrogen gas. And we're going to say that reaction has an enthalpy, delta H1. You might recognize that reaction as something we studied in class as a single replacement or single displacement reaction, where the metal comes in, displaces hydrogen gas, and in the process goes from an oxidation state of 0 to an oxidation state of +2. So it's a redox reaction. Okay, the second equation here has the same, but it's for the metal oxide. However, we want the metal oxide to be a product in our target equation. So what we're going to do is we can flip this reaction, and the flip reaction number 2 would behave as if the metal chloride solution is reacting with water to give us the metal oxide and the HCl. As we learned in class, when you flip an equation, you also have to switch the sign on the delta H. So this now becomes minus delta H2. So whatever the enthalpy of this reaction is, we're going to use the negative of. The third equation is here just because it's a very well-known equation. This is the equation for the formation of water. from its component elements, hydrogen and oxygen. And this will have a delta H3. And of course, as you see, it's already given, right? They gave us this value here already. So we'll incorporate later when we do our calculations, all right? So let's see what happens when I add up these three equations. Again, just like in regular algebra, anything that's on both sides of the equation can cancel out. So for example, the 2 units of HCl here will cancel out the 2 units of HCl over there. The metal chloride solution will cancel out with the metal chloride on the reactants side of the flipped equation number 2. The hydrogen gas product of equation 1 can cancel out with the hydrogen gas reactant of equation 3. And finally, the water in the reactants side of the flipped equation number 2 will cancel out with the water in the product side of equation 3. Let's see what we're left with. We have the metal as a reactant, we have the oxygen as a reactant, and we have the metal oxide as a product. So let's write out what the resulting equation is. So we have metal still standing, half a mole of oxygen gas still standing, and the metal oxide still standing. This is reaction number 4, so it would have a delta H4. And as you can see, that is exactly what we were looking for. So essentially, when we add up these equations to give us the one that we want, we are assembling a fictional path. It doesn't mean the reaction happens that way, but it doesn't matter as long as we have the correct reactants and the correct product. So what we're going to do then is we're going to add up the enthalpies. So the total enthalpy of this process would be delta H1 minus delta H2 plus delta H3, right? This is going to be delta H4, which by definition is the heat of formation of our metal oxide, okay? Now, what about these values? Where do we get them? Well, delta H3 is the heat of formation of water, which is given to us, so we don't have to do that one. It's already given to us. The ones that we're interested in are the heats of the reactions of the metal with HCl and the metal oxide with HCl. So these are the ones that we are going to have to measure. And that is essentially the procedures for today. This is what our lab is about. How do we find the enthalpies of these reactions? To do that, we're going to use a calorimeter. And a calorimeter essentially can be made by putting together a styrofoam cup. Actually, we're going to use a double styrofoam cup to be sure. We're going to even put a lid to make it even better insulated. And realize that in this situation, everything inside the calorimeter essentially retains all the thermal energy that's in there. So if our system is essentially a reaction that is happening in an aqueous solution, that means that the surroundings to our system are the solution and, of course, the inside wall of the calorimeter. Now, we're not going to measure what happens in the reaction. We're going to put a thermometer here in the solution, and we're going to measure what is the temperature change of the surroundings. That's what we're going to be measuring. Temperature change of the surroundings, all right? So what does it mean, for example? Let's say that the temperature change in the surroundings is positive. In other words, the temperature increases. Well, that means that the solution and calorimeter must have absorbed heat. Where did they come from? It must have come from our system. In other words, this would mean that we have a reaction that is exothermic. It put thermal energy out into the surroundings, and therefore cause them to increase their temperature. What would happen if delta T of the surroundings is negative? In other words, the temperature goes down. Well, that means that our system must have absorbed thermal energy from the surroundings, which means therefore that our system or the reaction is endothermic. Okay, so let's work on this now quantitatively. Remember, the coffee cup calorimeter is essentially what we call an isolated system, which means that all of the energy transactions are contained inside the calorimeter. Or as I sometimes say, what happens in Vegas stays in Vegas. What is the total energy exchange that happens in here? All right. Well, it would be whatever heat the reaction exchanges plus whatever heat the solution exchanges plus whatever heat the calorimeter itself exchanges. We have to include the calorimeter because the interior of the calorimeter is in contact with the solution and capable of exchanging thermal energy with it, right? Now, according to the law of conservation of energy, there should be no net change of energy inside here. This is because of conservation of energy, right? So that means that all of those energy exchanges add up to a net heat exchange of 0. So let's do this. Let's rearrange this expression so we can determine what is the actual heat of our reaction. Well, it would be minus the sum of the heat of the solution plus the heat of the calorimeter. And we have studied equations to determine those, and you'll recognize them. For example, for the solution, we're going to use the famous MCAT, I call it MCAT equation. So the heat for the solution would be the mass of the solution times the specific heat of the solution times delta T of the solution. So it looks like MCAT, that's why I call it that way. For the calorimeter, what we would have is the heat capacity of the calorimeter. In other words, the calorimeter does not have a specific heat. It's not like per gram of calorimeter. It's per calorimeter times the temperature change in the calorimeter. All right. So the first part of our experiment consists in finding out what is this value? What is the heat capacity of the calorimeter? And we have to find that by calibrating it. So we have to calibrate the calorimeter, which means we need to find out how much energy does the calorimeter exchange during a typical process. All right. So with these ideas in mind, what we're going to do now is I would like for you to make sure that you go back to our Canvas page. And in the next stage of the assignment, you're going to be watching a couple of videos by Dr. Mary Perot. She is going to demonstrate the techniques, the equipment, how to set things up properly for both the calibration and the chemical reactions we're going to study. And then how do we measure the temperature and determine the final temperature of our system? All right. So please go watch those videos, and then we'll be back to go over some of the calculations in the experiment. Okay, I'll see you soon.
Okay, so I'm going to go over an overview of these calculations, but remember, if you want more detail on them, we've got 2 20-minute videos that are posted on that YouTube channel, which Dr. DA goes through lots of great detail on them. And this is a nice experiment because you get the tour of the chemistry department, you get to see Dr. DA's videos and Dr. Perot's videos. We've already talked about what I want you to turn in with this lab. Now I want you to show you the calculations for part 1. So the calculation for part 1 is from your lab manual, and it is this guy right here. Actually, I just realized that I have a pointer here. So it is this right here, comes right from your lab manual. I just copied and pasted it. Now I want to show you what everything is in there. So first off, this one right here, T1 plus T2 divided by 2, That's going to be your average of cold and room temp water. So if we look over at your sample data, so here is your cold and your tap water. So you're taking the average of these two right here, and that is what goes right over here. So any questions on this right here, the T1 plus T2 divided by 2? Let me double check. Yes, it is recording. Yes. So video is definitely recording. Thank you. All right. So next up is TF right here. And TF will come from the graph, and I'll talk about the graph in just a moment. 4.184, that's your specific heat for water. And then 100 grams. So normally at this point, I would tell you to be really careful and try the best you can to get exactly 100 milliliters of water, which will translate into 100 grams. But now you don't have to worry about that. Dr. Perot very expertly poured that acid. That was quite a feat to pour from a large bottle into a graduated cylinder and hit the right mark at the same time. So here you have 100 grams because you used 100 milliliters of water. All right, so on the right-hand side, TR minus TF. So TR right here is your room temperature. And that is coming right up here, your room temperature. By the way, I'm using this little pointer for the first time. How is this going? Can you guys see the pointer okay? And is it driving you crazy? Would you rather see the highlight? You can see it? Okay. Do you guys prefer this here or for me to use a highlight when I'm talking about something? The highlights? Oh, okay. No worries. Good. I'm glad I asked. So let's go ahead and use the highlights instead. I was remembering there was some very old commercial for a car place and they had a little dancing dot. Anyways, we will highlight instead. Okay, any questions about anything that we talked about here first from this left-hand side? Okay. Now on the right-hand side, we talked about the room temperature, and that came, let me actually split right here. Come on, little guy. Yes, I do talk to my iPad sometimes. Gotta give it some encouragement. All right, so that room temperature was this right here, and it comes right over here. And keep in mind, you have trials 1, 2, and 3, and it looks like the room temperature is the same going across, but not all the values will be. So always be aware of which trial you're on. You are going to perform this 3 times, once for each trial. And then finally, oh, I'm sorry, before I say finally, we have TF. Oops. TF right here, that's going to come from our graph, and I'll talk about that graph in just a moment. And then right over here, this CCal. CCal you're going to be solving for, and once you find that value, it is going to be right over here. So T final from the graph, which we are waiting with bated breath to talk about, and then CCal, which is the answer to your calculation. And then once you get all 3 of the CCals, then you're going to average them. Okay, questions about anything so far on this calculation? All right, so right down here, it just defines everything. TR is room temperature. TF is T final, which comes from your graph. T1 is the room temperature of water. T2 is the cold temperature for the water. All right, so now let's talk about our scatter plot. So you have some experience doing a scatter plot from our previous lab. That again, if you want to watch someone do that graph and make it, that's what we have those other 2 videos for. And they will take you through a sample of actually calculating this and a sample of creating this graph. But here what you're going to do is you are going to have your temperature on the left-hand side, and you're going to do temperature in Celsius Down on the bottom, you have your time in minutes. Now, if you prefer your time in seconds, you're welcome to put it in seconds, but you have to either choose minutes or seconds. Occasionally, a student will do minutes and seconds, so like 6 minutes and 30 seconds, that does not graph properly. So you either have to choose minutes or seconds, and it looks like over here, we have all your time in minutes, so it'll be easiest to just do minutes this time. All right, so then you're going to create this scatter plot, and just like we've done in the past, you are going to ask the computer to give you y equals mx plus b, your straight line, and your r squared. So this is called the trend line. So you should be able to do it on Google Sheets, even if you don't have Excel. So what you're looking for your TF is this b right here. So for instance, if you had an equation like the one here, y equals negative 31.2x plus 21, it is that 21 that's your TF. So when it says plus and there's a number, that's the number you're looking for. That's what you'll put into your calculation. And it's also what you're going to put right over here for your T final. So that is called the y-intercept for those of you who love your math and algebra. But any questions so far on that graph? Okay, so what you're graphing, x-axis for all of them will be time. The y-axis will be temperature. So you'll be graphing this, and then for trial number 2, this, and then for trial number 3, this one and this one here. So I'm always available after class until 10 o'clock if you want to go over the graph together, or again, you can watch those videos that show you in detail and give you an example of how to do the graph. All right, so any questions so far on how to create the graph or anything else that we talked about? Okay. Let's see. So this is the calculation. Again, you're going to perform it 3 times. So once for each trial, and then at the end, you have your you have your C-cal, you did it 1, 2, 3 times, and then you're averaging it, and above the T final, that comes from your graph, because you have 3 graphs for part 1, 1, 2, 3 values here. Any questions on the value for this sheet right here? All right, so these would be your data tables, and so Dr. DA talked to you about these equations here. So I'm going to kind of skip what I would normally say about this equation over here, other than to say this is our Hess's law. So here you have reaction 1, 2, and 3. Reaction 3 is given. Let me get this out of our way. So reaction 3 is given, and it is 1 and 2 that you do experimentally, or you would have done experimentally. When you add them up together, you get the overall. And make sure you actually do Hess's law, as Dr. DA did in the video. So one of these needs to be turned around backwards so that the sum of these will equal that. So again, you're adding them up just like you did in Hess's law. All right, so now I want to go over your calculations for part 2. So Dr. DA mentioned that the idea is that normally our Q of reaction equals the Q of solution, just with opposite signs. However, we have a calorimeter that is not perfect. It is a styrofoam cup, and we splurge on you guys. You know, only the best for our students. We give you 2 styrofoam cups. But that said, it's still a styrofoam cup. Just to let you know, we're not being cheap. Even when I was a grad student at Notre Dame, the freshmen still got coffee cup calorimeters. But again, we splurge on you, and she didn't show it in the video, but we give you a double layer of aluminum foil. So only the best for our students now. But again, even at Notre Dame, they got aluminum foil for the lid. So this is a very common experiment. So the deal is that we actually want you to see what happens when the calorimeter doesn't work perfectly. So the calorimeter could either absorb some heat or it could put heat in. And often I find it depends on how hot the hands are of the person doing that swirling. So I always say in lab, try to find someone in your group who isn't normally very sweaty, because if you're really hot-handed, you will put some heat in there. But the idea is that all of the heat from the reaction either goes into the solution, meaning it's going into that water, or it's going into the calorimeter, meaning it's getting lost out from the calorimeter, unless you're very hot-handed, in which case it's going in. All right, so for our reaction, we're using the relationship Q equals MC delta T, or Q equals MCAT. So what I've done is I've broken down Q of solution into MC delta T, and it's negative because it's going in the opposite direction as the Q of reaction. So as the reaction releases heat, solution would be taking it in. Now the calorimeter has a slightly different calculation, and you might recognize this from when we talked about, give me 1 second, I just see the question coming in. So you might recognize that from when we talked about our bomb calorimeter. When we calibrate a calorimeter, it is Q equals CAT instead of Q equals MCAT. And the question is about, would gloves help to reduce the heat transfer? And if you're wearing heat gloves, absolutely. So basically, oven mitt style gloves would absolutely help that heat transfer, especially if you're very hot-handed. If you have nitrile gloves, which are the kind we normally wear in a chemistry lab, it's similar to the kind your doctors are wearing. Those don't really help very much. They make your hands pretty sweaty, so I would say that they definitely aren't going to help with the heat transfer, but any kind of a heat glove like a oven mitt would do wonders for it, yes. Okay, so what I've done is I've simplified the equation here, and this is the one that I recommend that you use. Those of you who are like, no, I want to do it all in its glory, you're welcome to use this one or even start at the very beginning. But I find that this simplified one works best. So you are trying to find Q of reaction, and that is the Q right over here. And what you're going to do is negative times delta T, and delta T will be your change in temperature, times M times C for the solution plus C for the calorimeter, and all of this is in joules. So let's talk about all those values. First of all, M is the mass of the HCl plus the solid. And I have it underlined because this often gets forgotten. You need to add up the mass of the HCl and the solid. So if I were to look, come on, little guy. There we go. Here I'm looking at the data for part 2, and I'm going to zoom in on this right here. So you're going to perform this calculation twice, once for each reaction. So here is a mass, and this is the mass for the metal. You've got to add in the mass of the metal to the mass of the HCl. How you're going to get the mass of the HCl is you're going to assume that Dr. Perot expertly poured a perfect 100 milliliters into her graduated cylinder, and then you're going to use the density right here to convert it from milliliters to grams. But don't forget, you've got to add them together. So that's a common mistake on this lab, is to forget to add in the solid. So you've got both the HCl converted into grams, and then the mass of the solid. So the one I highlighted is for your first one, but when you get to your second experiment here, you'll be adding in the mass right over here. Okay, any questions on coming up with that mass, how you're going to take the milliliters of HCl, convert it into grams using the density, and then how you're going to be adding in your metal or metal oxide? It is. Sorry if it's not very clear here. That is 1 point. Let me go ahead and write over here. 1.1187. Yes. So other questions so far? You're welcome. And you guys, if you can't read anything, please do let me know here. All right, so C for the calorimeter, this should be your average value from part 1. Normally, I don't let you go on to part 2 calculations until you've shown me your average value for part C, and that's because Sometimes experimentally we have some problems, but just to let you know, your C should definitely be a positive value. Normally we get our C values, they're between 20 and 80. So if you're finding a C value far off from that, send me an email and let me know. But again, this is the average C. This is this one right over here. So you need that average C in the calculations for part 2. So any questions about that average C? All right, so now delta T, our change in temperature. What we want you to do is take T final from your graph and subtract T initial, which is the initial temperature of the HCl. So T initial is going to be this HCl temperature before mixing. So this is T initial right here. So this right here would be your initial temperature. And then the final temperature comes from your graph. So you are again going to graph your data, or graph our data, I guess I should say. You're going to do the same graph that you did for part 1. So in part 1 you made 3 of these graphs. Now you're going to make 2 more, and you're going to do that again, the same graphs. And what you need is the TF right here. And that TF is your y-intercept. In terms of what it looks like in an actual equation, it would be this 21 right here. So if you had negative 31.2x plus 21, it would be the 21. Now I just made up that equation. Yours isn't necessarily going to be the number 21, but it will be in that position on the equation. So any questions on anything there? All right, so we talked about how to find CCal, how to find your change in temperature. All right, and we talked about how to find T final and T initial. So any questions about how you're going to solve this equation for Q? All right, so you need to solve this equation twice, once for the first experiment and once for the second. And when I say first and second experiment, I mean these two that are both part of part 2. So your first experiment would be with the calcium, and the second experiment would be with the calcium oxide. So at the bottom here, both of them have a place for Q of reaction. So you're going to list the answers to the Q's right down here. So that's why you have to solve it twice. Once for the calcium, once for the calcium oxide. All right, so next up, you need to convert your Q into a delta H. So delta H will be Q divided by moles of solid. And again, you did something really similar when you did your bomb calorimetry. So you are going to take Q divided by those moles of solid, and your delta H should be negative if it was exothermic, if it heated up. So make sure that you do list your delta H value as negative if it got hotter. And the way you're going to know it got hotter, I know you're not actually there live in person, but if you take a look at, it started at 23 and then it goes to 35, 38, it is clearly getting hotter. Again, you're starting with 23 over here and it goes to 24, 26. So again, it's getting hotter. So these are both exothermic reactions. So both of them should end up with a negative delta H. And I know it sucks when you just have to put in a negative when it wasn't there, but that's just sometimes the way it is in chemistry. I apologize. I know your math teachers would have a little heart attack over that. All right, so your delta H value, once you solve for it, it's going to go right down here. But before I leave this calculation, let me just remind you how you're going to find your moles of solid right here. You know how many grams of either metal or metal oxide you have. So in this case, we have 0.8142 grams of calcium. So you're going to turn those grams into moles by using your molar mass. The second time you do your experiment, you are going to turn 1.1187 grams into moles by using the molar mass of calcium oxide. So it's just a grams to moles conversion. So again, taking the Q that you've already found above from this calculation, dividing it by the moles, which you found from the weighed out grams and the molar mass. And then you're going to turn it into kilojoules because your first calculation gave you joules. First calculation gives you joules. We need kilojoules over here, so that means you're dividing by 1,000 to get from joules to kilojoules. By the way, if my zooming in and zooming out is driving you crazy and giving you a headache, please let me know. All right. Then you're going to use the delta H's in your Hess's law calculation. So you are going to use these values that you found way back up here so that you can solve your Hess's law calculation. So again, I'm going to refer you to the video that we just saw where Dr. DA took you through how to use these three H's to find what we really want, which is our delta H overall. And it's another way of saying delta H of formation because we are forming calcium oxide from calcium in its standard state and oxygen in its standard state. So this is kind of the big goal at the end of the experiment, finding that delta H of formation. And once you find it, it goes right down here, delta H of formation. So we got one more step to do, but any questions so far? All right. Okay, so I'm going right over here. So here it says delta H of formation. This is the delta H of reaction. This is your delta H reaction from the overall reaction. So that is the answer to your Hess's law. Then what we want you to do, it says percent deviation, but it's really a percent error because there is a known value here. And the known value is negative 635.5. Now, if this is a standard lab, you're doing it in class, I would tell you it's extremely hard to get something close to that negative 35.5. You're doing coffee cup calorimetry. Coffee cups are nowhere near perfect, so it's just really hard to get a good value. I haven't worked out the sample data yet. Another instructor came up with it, so I'm hoping they gave you good data that you will get a close value. But again, if it was a standard calorimetry experiment, I would tell you don't worry about having a percent error. Some people get up to like 50% error on this experiment. Again, it's just there's so many places where we could have problems with our equipment. You have just aluminum foil over the top. When you poke your thermometer through, it often creates a pretty big hole there, so we often lose heat there. Also, we're assuming you have a perfect 100 milliliters of solution. Most people cannot pour a perfect 100 milliliters like Dr. Perot did there. So just be aware of that. All right, so here in green I have the standard value right over here. This is your value. That means whatever you had here, you plug into your value. And here basically you want to subtract the two values and then divide by the accepted value and then multiply by 100. So if you get a negative, it just means your value is slightly shy of what it should be. If you get a positive, it means you're slightly over. As far as I'm concerned, you can use the absolute value because that just tells you how far off you were. But if you want to leave in the negative, that just says, again, your value is slightly under what it should be. But those are the calculations for this one, and there are no post-lab questions. So normally this isn't a favorite of students because in part one, you are just sitting there waiting for the water to, just measuring water over and over. And so sometimes that can be a little on the annoying side, but that's okay. Chemistry has a lot of waiting to do. When I took organic chemistry, they put our two labs on the same day and our lab lecture. So we had 8 hours of chemistry lab on a Friday. So we had 2 3-hour labs plus a 2-hour lab lecture. And there was no official break in there, so you just had to leave your partner watching the experiment, and you had to go out and eat really quick. So I definitely know what long labs are like. All right. Yeah. So any questions about anything that we've talked about, anything from those videos? Okay. So again, if you're thinking, hey, I would love to see someone actually work through a sample set of data, not this sample set of data, but another one, see someone build those graphs, we have 2 wonderful videos up here, and again, this is in our YouTube channel. If you haven't been there, through the videos link on our Canvas site, you can get to the channel, and then you can click on our playlist, and this is the playlist for Chapter 11. We watched the introduction and the lab demo. Those of you who are watching this later at home, please watch these first 2 videos. The second 2 are if you would like to see someone work through a data set and create a graph. So thank you very much for joining me.